Hello, and welcome to the Usefulati, the show that turns the writing of the world's most useful people into audio episodes you can listen to on your drive to work. Today we have a blog from Casey Handmer, the founder and CEO of Terraform Industries, a startup that's turning water and air into carbon-neutral natural gas with solar power. See the description for more, and let's jump in.
Or, how to explore the solar system and be back in time for Thanksgiving. It's no secret that I'm a space nerd. One of the major headaches of human space travel is that if you put the enthalpy of combustion, the melting point of metal, the Tsiolkovsky rocket equation, and the escape velocity of the Earth into a giant pile of nearly linear algebra and shake it for a while, it turns out that getting stuff into space is ludicrously hard. Launch from Earth to low Earth orbit requires about 9.3 kilometers per second of delta V. Low Earth orbit to Earth escape is another 3.2 kilometers per second. Going to other planets, even the closest ones by the most efficient, slow routes, takes another 1 to 5 kilometers per second. Getting back to Earth from Mars requires 6.5 kilometers per second, while getting from the Moon to Earth requires 2.3 kilometers per second. Delta V is produced by burning rocket fuel, and it accrues linearly with exhaust velocity but only logarithmically with mass fraction. This is the space equivalent of paying off student loans, and finding the principal has grown in the meantime. In practice, this means rockets have to be staged, with each stage contributing 4 to 7 kilometers per second. It is hard to imagine humans zooming all over the universe in giant General Systems vehicles if just launching to low Earth orbit, which is roughly equivalent to backing down the driveway, requires the behemoth two-stage Starship rocket just to get a few shipping containers to the edge of space. How to fix this? Maximize mass fraction and exhaust velocity. It's just rocket science. Both of these quests round to chemistry. If we want a radically more mass-efficient rocket, we need radically stronger materials. Starship is 9 meters wide with roughly 4 millimeters stainless steel wall thickness. As far as we know, there aren't any ways to make atoms grab onto each other much more strongly than steel. If we want a higher exhaust velocity, we need more energetic fuels. Starship uses methane and oxygen. There are a handful of chemicals with higher exhaust velocities, but their overall complexity imposes system-level mass costs that mostly cancel out their advantages. As far as we know, there aren't any ways to make atoms grab onto each other much more strongly than burning methane in pure liquid oxygen. The last screw to tighten is combustion efficiency, which is the most dark arts corner of rocket science. All the fancy pipes on these Raptor engines are designed to make sure that as much of the fuel's energy as possible ends up as directed kinetic energy. Burning the highest possible rates of fuel at the ideal ratios to completion at the highest possible temperatures and pressures. Last I heard, they're at about 97% efficiency. There's not much left to give. It's not hopeless. The Starship platform gives us the ability to lift 1 million tons of cargo to Mars at a fairly minimal cost. It's just that we can't hope to go much faster than 6 months door to door, even with the extremely shiny version 10 fully optimized design. This chart shows the delta V required to travel between Mars and Earth, together with transit time, as a function of departure date. It looks a lot like shipping schedules from England to Australia before the invention of steamships. Elon Musk has stated that there's no strong forcing function for better post-chemical propulsion systems until there's strong demand on the Earth-Mars route, and I think is right. But it's still fun to think about the next step on the tech tree. In some ways, we get to rerun the blue ribbon trophy that tracked 2 centuries of progress in transatlantic travel. There are a few options. Somehow, we need to get a much higher exhaust velocity. This means a higher temperature, a lower exhaust molecular weight, or both. There are a few approaches: electrical propulsion, fission, fusion, or antimatter. Electrical propulsion is the least exotic of these. It's used by Starlink to maintain its orbit. Electrical propulsion can achieve extremely high exhaust velocity, allowing very high delta V designs with sensible mass fractions. Unfortunately, its thrust density is very low, so it is not fast. There are some speculative designs that employ enormous solar arrays or space nuclear power reactors, but even these don't have the sort of thrust that is easy to achieve with chemical propulsion, and as such are unlikely to be competitive on the Earth-Mars route by transit time. Fission propulsion has been tested in programs both in the United States and the USSR. A nuclear core heats a stream of hydrogen, whose low molecular weight can achieve an ISP of about 850 seconds, good enough to get to and from Mars in just 4 months, albeit with slightly radioactive exhaust. The metals required to build a nuclear reactor are not as thermally tolerant as Inconel, so nuclear thermal does not achieve chemical propulsion exhaust temperatures. It also requires building, testing, qualifying, and flying a nuclear reactor, whose associated mass has a steep penalty. The other kind of nuclear fission propulsion is Project Orion, very cool, but probably beyond the Overton window. But probably unbeatable if we needed to move 1 million tons to Pluto as quickly as possible, regardless of damage to Earth's crust. Nuclear fusion propulsion, based either on magnetic or inertial confinement, is attractive relative to Project Orion for less fallout, higher energy density, but suffers from similar thrust density problems to electric propulsion. It also suffers from fusion's noted inability, thus far, to generate a self-sustaining reaction. So things stood, in my mind, until I recently was inspired to take another look at exotic space propulsion methods. Antimatter is simply matter with the opposite charge to ordinary matter, generated rarely in high-energy nuclear reactions, with the neat property that when it collides with ordinary matter, it turns more or less completely into gamma rays via annihilation. Fission and fusion must be content with mass-to-energy conversions of a paltry 1% or so. Antimatter achieves 100% with psychotic levels of dedication. In practice, this means it could be a far more effective source of propulsion heat than nuclear thermal. In a recent post on solar investment opportunities, I listed antimatter production as a somewhat tongue-in-cheek application of roughly unlimited quantities of incredibly cheap solar power, along with synthetic fuel for 8 billion private hypersonic jets, 10 petawatts of artificial intelligence training compute, and enough desalination to perform a real-time simulation, actual size, in place, of the global hydrological cycle. Jenny Chase, the legend who runs BNEF's solar prediction team, took exception to antimatter production, as though any power source other than solar could do this. Hell, about 3.8% of the sun's energy comes from positron annihilation as part of the proton-proton fusion chain. Around this time, on Patio 11's recommendation, I read Theft of Fire by Devon Erickson, the first post-SpaceX hard science fiction novel I'm aware of. It's a very fun read, pulp plus hard science fiction, no mean feat in a book universe with relativistic propulsion, an audiobook Kickstarter in the works. It induced in me a deep craving to see the rings of Saturn with the unaided eye, something that's not going to happen if we remain imprisoned on this rock by our puny rockets, strong gravity well, and inability to efficiently convert capital into self-replicating robots. Back to antimatter. It's ludicrously expensive and difficult to make, nearly impossible to store, and just makes a bunch of hard gammas. It's so ornery, the only thing it could possibly be good for is a high-performance rocket propellant, since chemical propulsion is perfectly adequate for cars, boats, and planes. All these problems are problems that can be solved on Earth, though. Antimatter does not require us to figure out how to make, for example, a fusion reactor operate in space. Once we make it on Earth and solve storage, we can transport its absurdly high value on rockets into space and use it there. As a rough rule of thumb, doing this is 1 million times more expensive than on Earth, which creates a strong economic incentive to move any production difficulties back to Earth. For example, modular space station construction was a mistake. At any price, it would have been cheaper to design a bigger rocket to launch a space station in one piece. Let's run a basic first principles estimate of the performance of a Starship-scale rocket using antimatter fuel. For reference, Starship contains about 1,200 cubic meters of fuel and oxidizer. Liquid methane and oxygen have a similar density to water, about 1 ton per cubic meter, for 1,200 tons of fuel and oxidizer, split roughly 240 tons of methane to 960 tons of oxygen. Oxygen is a lot heavier than hydrogen. Our model for an antimatter engine is that a stream of antihydrogen atoms are electrically beamed into a block of refractory, high-temperature material, which absorbs the resulting gammas, getting extremely hot. The propellant, hydrogen by default, but water could also be used, flows through this block, absorbing the heat and then expanding through a standard rocket nozzle. There are various ways one could make even hotter exhaust, via radiative reheating, or using regenerative cooling to keep the block below its melting point. There's also a light-only propulsion option, with far higher ISP and far lower thrust. For now, we'll just look at the simplest approach. The carbides have extremely high melting points. Some combination of hafnium carbide and tantalum carbide may achieve a melting temperature of 4,000 degrees Celsius. It is quite difficult to characterize material properties at this temperature. So let's make our refractory block out of some exotic carbide and call the operating temperature 4,000 Kelvin, a few hundred degrees cooler. We're also going to wave our hands about chemical stability in the presence of superheated hydrogen. Under these conditions, we can achieve an ISP of about 1,700 seconds, helped by the hydrogen dissociating at high temperatures. How much antimatter is needed to heat 1 ton of hydrogen from cryogenic liquid to 4,000 Kelvin? About 300 micrograms. 1,200 tons of hydrogen requires 360 milligrams of antimatter. If that antimatter is cryogenically frozen solid antihydrogen, it occupies about 4 milliliters. Somewhat less than a teaspoon of the worst ice cream ever. That's a 10 billion to 1 mass lever. A standard Starship, 1,200 tons of propellant plus 100 tons structure plus 100 tons of cargo, 370 seconds ISP Raptor engine, can achieve about 7 km per second of delta V. Just enough to fly from Mars back to Earth in a single stage. The same masses, but this time with hydrogen propellant and antimatter heating, could achieve 32 km per second of delta V single stage to orbit? Single stage to Mars and back, 7 weeks each way, on a single tank of gas. If we're able to refill the hydrogen propellant in low Earth orbit and on Mars, we should be able to shave the trip time down to about 5 weeks during the launch window. Not bad going for a rocket engine with no moving parts. Further improvements will require exhaust reheating or some kind of exotic gas core. If we can bump the ISP up to 5,500 seconds, non-trivial, the trip will take just 14 days each way, with a 90-minute 1G burn at each end. 105 km per second of delta V. This is approaching fundamental physical limits of performance. Some kind of alien fusion core, for example, like in Theft of Fire, capable of arbitrary impulses up to the endurance of the passengers, flying a brachistochrone trajectory could achieve the Mars-Earth flight in 43 to 112 hours, depending on planet positions, at a comfortable 1G, or 19 to 50 hours at a miserable 5GS, with a maximum speed of about 1.5% of light speed. Okay, I'm sold. How do we make this happen? Mass-producing enough antimatter to fuel starships and storing it for use is considered extremely difficult. There are multiple challenges. Fortunately, many of them can be approached piece by piece, or with cheaper physical analogues to determine if progress is possible. Here's a great recent X-thread on antimatter production. The upshot is that we currently do it with particle accelerators. Tevatron produced 2 nanograms, or 360 kilojoules, per year. A 30 kilowatt beam consumed 1 terajoule in a year, for a total production efficiency of 1 to 2,620,000. Not great. But not terrible. If we take our usual rule of thumb that doing stuff in space is 1,000,000 times more expensive than on Earth, this production efficiency is actually okay, especially considering the otherwise unattainable performance we can get for space propulsion. 2 nanograms per year isn't a lot. It's enough to heat about 6 grams of hydrogen propellant. But at this point, we haven't really even tried to mass-produce antimatter. Our position reminds me of the opening briefing at Los Alamos in Nolan's Oppenheimer film, where just a handful of marbles represent the current stockpile of uranium and plutonium. By 1985, the human race had churned out enough for 63,000 warheads. Given that the mass energy of protons is 938 megaelectron-volts, it's possible to build a much cheaper, more compact accelerator at that resonance, rather than copy-pasting the Tevatron 100,000 times. Not that that wouldn't also be cool. It might also be possible to mine antimatter from the Van Allen belts. Once we've made antimatter, we need to store it. In particle accelerators, it's accumulated in electromagnetic storage rings, but this won't work for space applications. It's too heavy and bulky. The crazy idea I'm toying with is taking a stream of antiprotons, gradually cooling them, condensing them, and freezing them in a tiny chip of mostly neutral antihydrogen ice. A positron source, for example, fluorine-18, is used to regulate surface charge on the ice chip to enable an active electrostatic suspension system to be used. If we get it cold enough, the vapor pressure and surface tension, itself a function of net charge, can be regulated to control the rate of off-gassing or antiproton release. As long as the loss rate is lower than the heat removal capacity of the vacuum containment vessel, all is well. The physical size of this system could be quite small. A Starship-sized rocket only needs a teaspoon of antimatter. The vacuum chamber must have various support systems. Vacuum pump, refrigerator, staged Peltier cooler? Or must we wrangle liquid helium? We will have liquid hydrogen around. A reliable, simple control system. An electrostatic tunnel to manage charging and antiproton removal. This tunnel must convey cold, slow antiprotons to the refractory block, where they annihilate, producing gamma rays, which are stopped with a few inches of carbide material. The engine itself can be relatively compact, though somewhat larger than an RCS thruster. Even better, this storage system can be tested with regular hydrogen and regular electrons by changing a couple of signs. Antimatter is highly energetic, so safe storage is a concern. Contrary to intuition, sub-gram quantities don't pose a risk of punching holes in the crust or deorbiting the Earth into the Sun. It contains enough energy to heat 1,200 tons of hydrogen to a few thousand degrees. That is, roughly the same amount as a fully fueled Starship, and quite a bit less than fission atomic weapons. If catastrophic containment loss occurred, the antimatter would begin annihilating with the walls of its vacuum container, generating a bunch of gamma rays and heat. The gammas are extremely unfriendly up close, but dissipate according to the inverse square law, passing through many meters of air before interacting. The heat will swiftly destroy the physical apparatus, dispersing the regular matter that the antimatter needs to annihilate with, slowing the reaction. If, hypothetically, the antimatter storage device was kept on a tall tower in a remote area, or perhaps suspended far beneath the surface in the open ocean, surrounded by effectively infinite thermal mass, a worst-case scenario is significantly more benign than any kind of nuclear or conventional weapon, all of which dump most of their energy into heat, light, and blast waves to maximize physical destruction. Two key problems here: production and storage. Both to be solved piecemeal on the Earth. From my perspective, both seem to have acceptably effective solutions that are far easier than building and certifying a high-performance nuclear thermal drive or space fusion drive, let alone Project Orion. As soon as neutrons are involved, things get very messy. In contrast, the flying part of an antimatter rocket is simple compared to even a chemical rocket. What's it going to take to make this happen?